So my co-chair
Thank you.
will be speaking now, progress understanding lunar oxygen extraction with the FFC process. So feel free to share slides and take it away.
Thank you. I would like to share with you the work I've been doing with my colleague at ESA and regarding the progress we did on this FFC process. So for those who are not familiar, the FFC Cambridge process is an electrolysis process where you insert your regolith as a cathode inside the molten salt. Usually it's based on molten calcium chloride. And then by applying some current between this cathode and an inert anode, or for laboratory or terrestrial application, a carbon anode, you can extract your oxygen directly by direct deoxidation. So then you will have your oxygen traveling to your anode, and I would guess as CO, CO2 if you have a carbon anode. But of course, on the moon, if you are interested in the oxygen, you will then use an inert anode to recover your oxygen as O2. So far, that's the only process who has shown, to our knowledge, the possibility to extract 100%. So the totality of the 40 to 45 weight percent of the regolith is oxygen. So this process has shown that you can extract all of it. So you end up with a byproduct, then you end up with a metal powder. So I think this slide, this picture of this regolith before and after has been shown by quite some people in our management before. But just to make things clear, this is really all the metals. It's not only titanium. So we are not relying on ilmenite or specific mineral, but we are really able to extract the oxygen from every silicates and every mineral on the moon, to our knowledge. So the mixture you get in the end is a mixture of silicon, calcium, aluminum, iron, magnesium, and titanium. So at ESA in Netherlands, so at the center is called ESTEC, we have different equipment for advancing the research. So we have like 2 FFC reactor where we could have sample between 10 to 30 grams of lunar regolith. We have a mass spectrometer to analyze the gas we extract from it. But it's always good to cross-check what you have, the oxygen you have left in your material. So for that, we have a quantitative oxygen analyzer where we add some tiny piece of sample of partially reduced or fully reduced sample after it was processed by the FFC, and we can see how much oxygen was left inside. And for other testing and quick testing, we have a smaller scale setup. So the focus of our research was trying to lower the temperature of the process. Currently, it runs at 950 degrees, but at 950 degrees in calcium chloride, you have many issues regarding the material you can use for the anode, for the reactor. It is quite corrosive. And by lowering the temperature, you increase the number of material you could choose for every element you have in your cell. So we kept the same baseline, which is a 24 hours experiment of 24 grams of regolith. And we know that with this baseline, we can extract about, in principle, 1 gram per hour, so 100% of the oxygen. And we run, the baseline is also at 950. So then what we change, we try to find a way to lower the melting point. You can, since the melting point of calcium chloride is at 770 degrees, you can already get some margin here, but otherwise, if you want to get lower, you need to mix the salt with different one. And that's why you have eutectics as eutectic points when you mix calcium chloride with sodium chloride, potassium chloride, or lithium chloride. So we now have different temperature where we can run at 680 degrees, 806, and 660 degrees, which was the lower temperature we tried with this different technique. And the result we got are on this table. So what you can see here is as we use pure calcium chloride, so when our baseline, we are close to 100% reduction with close to 90%, and with this 24 hours baseline. And as we reduce the temperature, we also lose in efficiency as we get closer to this 50% removal at 850. But by using eutectics, actually, we stay in this band of 40 to 50% reduction while still lowering the temperature. So really, now we have basically a process which can extract 40% of the lunar regolith below 700 degrees. So if you compare the yield or the recovery you can have with the hydrogen reduction or carbothermal reduction, that's actually in principle much better. Regarding the Faradic efficiency or current efficiency, so what is the role of the electron we use to extract oxygen? Actually, it drops quite a lot in pure calcium chloride. But actually, we have some salt mixture where we kind of reduce the parasitic reaction that can happen with dissolved calcium or with the carbon anode we use for our experiment, and we can get a better use of our electrons. So in principle, we waste also less current in the process. So that's basically what you can see here. We also made an experiment with pure lithium chloride just to show that also the impact of calcium of calcium chloride in the salt on the reduction process, as just having a pure lithium does not give more than 20% reduction. So regarding the material aspect, what we actually recover. So when you have like close to full reduction, you can clearly distinguish some different phases in a grain of material extracted. So it's not usual alloys that you will get. It could be, for instance, calcium, silicon, aluminum, or silicon, magnesium, or iron, titanium, silicon, aluminum. And that's why, so now we are investigating also what we could do with this powder. Either we could try to oxidize it again and do maybe some metal fuel, or to try to 3D print it. So these are still open, and that's another branch of research. So regarding what's the problem comes more when we have a lower reduction. So even at 40 to 50%, it's much harder to distinguish what exactly happened to the material, as the oxygen extracted probably comes from a bit every mineral, but not to the point you can actually distinguish metal phases. So here by ACM, we could distinguish maybe a partially reduced olivine, some metal phases, but at very small pockets of silicon calcium or silicon titanium iron. But it was not, basically with every, and this is just an example, but we had the same with the other partial reduction. It's really hard to follow exactly which mineral we use first and have these different steps. So we need to maybe try to have single minerals and see what happens to them to understand exactly what's the reduction process at the mineral level. So if we can just make a small trade-off table from this result, if we still get higher temperatures, so far we feel that we still have higher yield, and this is still well-studied system. All terrestrial systems are still working at 950 degrees. But as a cons, of course, we still need to solve the material challenge regarding the anode and the reactor, and of course it's more energy for melting the salt and then maintaining the temperature of the system. At lower temperature, we see that we still have a quite good reduction if you're interested in the oxygen, but you so far don't get the metal. However, you have to keep in mind that these are all 24 hours experiment. It's not, so the 40% reduction we got at 660 degrees, for instance, it might not be the maximal reduction. By making it 48 hours, we might get much higher reduction. This we'll have to try later to see if there is a ceiling at this reduction, or if we can also get a full reduction below 700 degrees. So that would be the next step. But so far we see that we have higher current efficiency. That's also quite an advantage. And also with a lower reduction, if we don't have a full reduction, the calcium also plays a role, as it can form intermediates during the reduction process. And then maybe if you partially reduce your oxide, the calcium is still in your structure. So over time, if you take out your regolith, you lose a bit of calcium. So this we have to understand that, of course, we don't have any consumable in the system. Otherwise, we lose a strong asset of using this system.
Less than 1 minute.
Yeah, perfect. So let's leave 1 minute for questions. Thank you for your attention. And yes, if there is any question, feel free to ask.
Thank you. There's been some good discussion in the chat, so maybe you can answer some of those. There's one question that was from both Carl Hibbets and Laszlo Keste, similar question. How much electrolyte do you need to obtain a certain amount of oxygen? So how efficiently can the electrolyte be recycled?
Yeah, so I don't know if you still see my screen. I try to stop sharing actually, but yeah, just so I can see the chat. Yeah, so currently we have the baseline is 1 gram of regolith for 33 gram of salt. So we have 33 times more gram of salt than a gram of regolith. It's a batch process. We try to reduce this ratio. Of course, the salt is not a consumable. So but if we can try to bring as little as possible to the moon, it's of course beneficial. But that's one element of the research as well, trying to lower maybe 1 to 10 or 1 to 20 ratio is what we see feasible. Below, probably not, just because of the volume of the soil itself. But that's where we stand at this moment.
Okay, great. And there's one more question from Michael Nord about scaling, but maybe we can answer that in the chat and in the discussion after this session, because we really need to move on to the next talk.